discussing white noise. So white noise has uh, an impulse autocorrelation function or correlation function. This is also called autocorrelation, okay? Because we are correlating the process with itself. Okay, so it has a delta function or impulse function. We know that when t is equal to s, we have this delta function, and for other values of uh, t, it is 0. Now we also know that this C1 is nothing but the area under the delta function, because if you consider the triangular function, it is 1 over epsilon here, and then here it is minus epsilon to plus epsilon. Now as epsilon goes to 0, so in the limit we have the delta function, right? Now as epsilon goes to 0, this amplitude becomes very large, right? So a delta function actually has infinite amplitude, but the area under the delta function is unity, and when we have a scale factor, then the area is given by that scale factor. And the convention is that the arrow length is actually the area under the delta function, which is shown here for this particular case, and it is C1. But if you consider the amplitude of the delta function as at t is equal to s, it is actually infinite. So at t is equal to s, the white noise has infinite autocorrelation. For other values of s, it has zero autocorrelation, zero correlation. So it means that it is highly correlated when t is equal to s, but it is not at all correlated when t is not equal to s. Okay. Now, for this kind of autocorrelation function or correlation function, what kind of power spectral density should we expect to see? So for now, in this case, we know that the condition that we need to check holds, because the autocorrelation function, the correlation function, uh, uh, if we integrate it from minus infinity to plus infinity, it actually exists. So we can take the Fourier transform of the autocorrelation function to find the power spectral density. So phi xx, if when we are considering single dimensional case, we know that it exists only when tau is equal to 0 and area under the delta function is unity. So we basically get C1, right? When tau is equal to 0, this actually is unity. And if you put the function C1 times delta function, C1 will come out. So, and the area under the delta function is unity. We basically get C1. So the power spectral density actually has a flat profile. So this implies that all the frequency components are equally important here, right? So white noise has infinite bandwidth. How about power? Now we know that if we integrate the power spectral density over the entire frequency range, we get power, right? So this gives us power. In this case, we just need to put C1, and then if we integrate it from minus infinity to plus infinity, we get actually infinite power. So it has infinite bandwidth and infinite power. For a random process, its power is actually given by its variance. So does it have infinite variance? Yes, it does. As I told you, this has infinite amplitude, right? So at t is equal to s, it has infinite variance. Now a process which has infinite bandwidth and infinite power cannot exist in reality. So it is actually an abstract mathematical concept. Pure white noise does not exist in reality. Okay? Now why is it called white? Because it has all the frequency ranges. It includes all the frequencies, frequency components, and that's why we call it white. White noise, just like white light, white noise. But it does not exist in reality because we cannot generate a process with infinite power. We can have a process with infinite energy, as we have seen with periodic signals. They have infinite energy, but they cannot have infinite power. We cannot pump in infinite power. So pure white noise does not exist in reality. But what does it mean? Does it mean that we do not have white noise at all? Actually, a finite bandwidth process can be approximated as white noise if its bandwidth is larger than the bandwidth of interest. So if we have now we are considering the power spectral density, okay? So let's say we have a process like this. Bandwidth means we are considering 3 dB bandwidth. So let's say this is the bandwidth of the process and we call it delta F2. Okay, and the bandwidth of interest is actually this one. This is delta F1. Now this process, this one, we approximate as white noise. Let's consider an example and we can use this one only, this class. We know Y is the measurement, S is the signal or the variable of interest which you want to estimate, and N is noise, the measurement, actual signal and noise. Let's say S has this bandwidth delta F1 and N has bandwidth delta F2. Okay. Now, if you look at the autocorrelation function, this is the power spectral density function. If you look at the autocorrelation function, when you have a finite bandwidth process, the autocorrelation function will not be an impulse function. It is correlated in time. So let's say we are plotting the autocorrelation function Rxx t minus s or t is equal to s. So let's say we are plotting is s, and when this is where okay. Now if you plot the autocorrelation function of this finite bandwidth in, you'll find that it has a profile similar to this. May not decay the way I have shown, but it will decay over time as S increases, as S goes away from T. Okay, and you will find that it has appreciable or significant non-zero value over this interval 1 by delta. Sorry. So this is approximately, you will see, 1 by delta f2. Okay, so beyond 1 by delta f2, it basically has almost zero values. Now, when we are actually using this one, when we are making measurements for this signal or quantity S, we need to discretize it. We cannot make measurements in the continuous one. We need to discretize it. Therefore, we need to actually draw samples. Now, when we draw samples, we need to actually sample the whole thing at some interval. Now, to preserve the bandwidth, since the bandwidth of interest is delta f1, preserve the bandwidth, the sampling interval delta t must be greater than delta f1, 1 by delta f1. Otherwise, we will distort the signal of interest. S will be distorted in the discrete samples. If we choose the sampling interval lower than this value 1 by delta f1, we will distort this load. We do not want to do that. We want to preserve all the information as it is. Therefore, we must choose a sampling interval which is greater than 1 by delta f1. Now, we know that 1 by delta f2 is less than 1 by delta f1. Right? So, if the first sample is picked here at this point, S is equal to T, the next sample will be outside this interval where the autocorrelation function has some significant non-zero value. So it will be, let's say, somewhere here. The next sample will be at this point. Right? So what can we say? We can say that N has some non-zero value. Its autocorrelation function is non-zero for the first sample. But for the next sample onward, because all of them will be now outside the region where it is non-zero, the autocorrelation function is non-zero. So for all other samples, if you try to correlate this with this one, you'll find that it has zero correlation. That's what the autocorrelation function shows. It has zero correlation. So if you keep sampling Y, you are getting corresponding samples, but those samples will not be correlated. Therefore, we can approximate N as white noise. Does it make sense? Is this clear? If you do not understand, ask me. Do you understand why N is approximated as white noise? Yes or no? If you do not respond, what should I interpret? You do not understand anything at all?
Yes, ma'am.
I'm not getting response from anybody else. Only Apurv said he understood. How about others?
Yes, ma'am.
See, if you do not understand something and keep quiet, you will not be able to answer questions in the exam. Keep that in mind. Even if I ask straightforward questions, you will not be able to answer. Now, an example, real life example of such band limited process, finite bandwidth process approximated as white noise is this. Uh, background noise in recorded audio signals of poor quality can be approximated as white noise. So if you replace such recorded audio signals which do not have good quality, you will hear some hissing sound in the background. Okay, that hissing sound, which appears to be some sort of noise, background noise, can be modeled as white noise. And in this particular case, this white noise has the entire frequency range of audible signals. It has the entire okay, so that is from 20 hertz to 20 kilohertz. So the white noise, the background noise has this entire frequency range. So over the entire range of audible frequencies, it has a flat profile. Whereas the signal of interest, the audio signal, the recorded signal of interest will occupy a portion of the audible frequency range. Okay. So that's all about white noise. Often uh, we model noise as white because the bandwidth of the noise, the error, the measurement error, is more than the bandwidth of the signal. Okay? Therefore, the measurement error can be modeled as white noise. Next, I'll quickly tell you about this matrix U and not. So, it is actually carrier power to noise power spectral density ratio. Okay, so we know how to define the signal power. We already discussed how to define the signal power even for a deterministic signal. The same definition holds here. Okay, and then noise power spectral density. So we know how to define noise power spectral density. So it's basically the ratio of the carrier power to the noise power spectral density. Okay, and it quantifies the quality of signal received. Okay, I already gave you the range of CO and not that we generally see in the signals, and by seeing CO and not we can easily make out whether we have received good quality signals or bad quality signals. Now this is expressed in logarithmic scale. Okay. So what is the, now we know that the unit of power is what? What is the unit of power spectral density? On the left side we have watt, and then on the right side we are actually integrating the power spectral density over the frequency range. So it must have a unit of watt per hertz, right? So we have watt in the numerator and then watt per hertz in the denominator, and that will give us hertz. Now since we are taking a logarithm, okay, so the actual ratio C by N naught has unit hertz, and then we are multiplying log 10 and then 10 outside. So this gives actually dB hertz. Okay, this is why the unit of CO and naught is dB hertz. So you will see 40 dB hertz, 30 dB hertz, 25 dB hertz, and so on. By the way, for the project, you should start working well in advance. Otherwise, towards the end, you will not be able to make things working. And there is no compensatory presentation for the project. I have already told you the date well in advance, and it will be held on 11th March. Any question? Anything you want to know about silver and not or related things? Okay, next we are going to look at some filtering algorithms. This is the last part of this topic. Now we know that a filter in the context of navigation is an algorithm that estimates some unknown quantities from a set of measurements, eliminating noise as much as possible. Right? There are many filtering algorithms. We are going to look at 4 of them. The first one we'll consider is called minimum mean square error. Estimator. A filter is also called estimator because it estimates some unknown quantities. Next, filtering algorithm or estimator we'll consider is called weighted least squares. WLS. Third one is linear. As I told you earlier, in the context of that example, that MMSE is not a linear estimator. it's not guaranteed that the estimated quantity is a linear function of the measurements. Uh, Therefore, we have this linear MMSE where we impose that it has to be a linear function of y. Okay, linear MMSE with batch measurement, with a batch of measurements. We are going to see the implementation of linear MMSE with a batch of measurements, which we also called a batch estimator. The fourth one is Karl filter. Now in this class, due to time constraint, this is not about filtering and estimation. We are just discussing it because you need to have some background of estimators to understand concepts of navigation. So it's not possible to discuss about all these algorithms in detail. We are going to look at the derivations of the first three filters, first three estimators. The fourth one will not be able to discuss in the class, I mean the derivation part. I will note the questions of a column filter, and if time permits, I'll also quickly tell you about some important properties. But I'll give you the derivation. There are different ways of deriving the column filter algorithm. I will send you the simplest one over email. Don't think that just because we have not discussed this in the class, your questions cannot be asked from the derivation. So you need to study this on your own. Okay, the derivation of the column filter equations need to be studied by you on your own. It will not be discussed in the class. Okay, but whatever material I will give you is straightforward, easy to understand. If you spend some time, you will be able to follow the derivation. Okay. But the other three algorithms are easy to derive, and we will derive them in the class. Okay. The first one is MMSE, minimum mean square error estimator. Minimum mean square error. So as the name suggests here, actually you want to find an estimate of the unknown quantity by minimizing the mean square error. So what is the mean square error? Let's consider a scalar case, simple case. So let's say x is the, let's say it's a random variable which you want to estimate, and x hat is its estimate. Now x hat is a function of y. We are making measurements, and the measurements are denoted by y. So x hat is a function of y. Now we are interested in minimizing the magnitude. It does not matter whether it is plus or minus. Okay, we are interested in the magnitude. We want to reduce the absolute here. So to eliminate the sign, we square it. Because it is scalar, we square. Okay, and then it's a random quantity because x is a random variable, and then y will also be random. Okay, so basically it is a random quantity, and we want some deterministic parameter. Now we know that if we take expectation, which is nothing but average, weighted average, so expectation of these we get a deterministic parameter. So this one is what we are interested in. And we want to make it minimum. We want to find x hat in such a way that this quantity is minimized. So this is what we do for a scalar case, single dimensional case. Now what if x is a vector? If x is a vector, then we can take this one. We can transpose it, and then multiply it. with the original loop. So this whole thing we take and then we apply the expectation operator. So this is for a scalar and this is for a vector. Okay. Whatever we are going to derive, we'll use square, but the same derivation also holds for this one. Okay. So our cost function here G is J, and it is the mean square error. This is what we want to minimize. Now, since we have applied the expectation operator, we need to do some integration, and we also need to pick the corresponding PDF probability density function. Right? Now see, x is a random variable, so we require each probability density function. X hat is a function of y is again a random variable. So we have two random variables basically. So to find the expectation of this, we need to do double integration. And we require the joint PDF. Right. Now we can write this joint PDF as conditional PDF and marginal PDF, product of the two. So let's do that. Now in this case, y is assumed to be given. For this case, y is not a random variable, only x is a random variable. We have this one for the first integration, and then for the second integration, it is y is treated as a random variable. Now we are interested in minimizing j and find the corresponding x hat. So we need to take the derivative of j with respect to x hat. Then only we can minimize and that will be equal to 0. So this is what we are interested in. We want to find x hat in such a way that the derivative of j with respect to x hat is equal to 0. Now if we look at the expression of j, this is a function of x hat, so this one will have a contribution, but the other terms will not have any contribution because they are not functions of x hat. So if you take the derivative of the right hand side with respect to x hat, you basically get 2 outside and then this term, right? Because we have square, so the derivative of this whole thing, this one, will be 2 times this one again, right? So what we have is this one, 2 x minus x hat. I'm dropping y from the argument of x hat for simplicity. And then we have this conditional density. This is equal to 0 and this is equal to 0 for any y, So this is 0 for any y. Now for this to be 0 for any y, the only possibility is that this is equal to 0. Because this inner integration is for a given y. So the inner integration must be equal to 0 for any y, right? This is equal to 0. Now we can separate the two terms. So on the left side we have this. Now in this integration, y is treated as given. So x is the random variable. So what is the left side equal to? What can we write about the left side? If x is given, y is given, and we are doing the integration with respect to x, so what can we write about the left side? Tell me quickly, you don't have any questions, so I assume you are following everything. No questions indicate two possibilities. Either you are following or you are not following at all. So tell me what the left side is equal to. You do not know? Didn't we discuss how to find the left side? You are doing the integration with respect to x. And x side is a function of y. So what is the left side equal to? And you are doing the integration from minus infinity to plus infinity, of course. Tell me what the left side is equal to. Hmm? Nobody can answer this question? Are you following what is being told? You are not following, you simply you're just there.
Ma'am,
Yes.
is it expected value of x hat?
What is that expected value of x hat when y is given? X hat is a function of y. Are you doing the integration with respect to y? Tell me that first. Are you doing the integration with respect to y?
No, ma'am.
Then you are doing the integration with respect to x. And x hat is a function of y. So what will you do? You just follow the simple rule of integration and some important property of the probability density function. That's it. So if you are not doing integration with respect to y, what will you do with x hat? How can you use x hat for the integration? What will you do then? Nobody can answer this question. Should I assume that you are not following anything? If you cannot answer this question, then that only I can interpret. You are not following anything. What will you do with x hat? If x hat is a function of y and you are not doing the integration with respect to y, what will you do with x hat?
We will write it outside the integral x hat
Yes, yes,
integral
yes.
minus infinity to infinity fx given y dx.
What is that equal to? If you apply some important property of the PDF, probability density function, what is that integration equal to?
1
1. The left hand side is x hat.
x
How
hat
about
is
the right hand side? What can we write about the right hand side? We already discussed this in the class. So multiplying x and then we have conditional density. Integrating from minus infinity to plus infinity. What is that equal to? Hmm? There's a particular name for this expression. What is that? You are using conditional density. If you do not use the conditional density, if you use some PDF, it has to be a PDF of x, right? Then what is that equal to? The right hand side expression?
Ma'am, that is a conditional mean.
So this is conditional mean. So x hat, the minimum mean square error estimator is nothing but the conditional mean. Last week we discussed a simple example using the PDF. So in that example also we found that the estimate is nothing but the conditional mean, because we calculated the conditional density and then we found the mean and variance of conditional mean and conditional variance, and the conditional mean is this. And then we discussed some properties. And I also told you that later you will see that this condition, this is actually minimum mean square error estimate. Today we derive the expression for minimum mean square error and we find that it is nothing but the conditional mean. So what we discussed last week is actually minimum mean square error estimate. So whatever properties we discussed in that example hold for minimum mean square error estimate. It applies appropriate weights to measurements and a prior information uh, and then finds an estimate. So that is an inherent property of a minimum mean square error estimate. Here we see that x hat is expectation of x given y. Okay, so this is only minimum use parameter. Okay. Now, when we are estimating something, we are interested in the estimation error. Estimation error it's denoted as epsilon, can be written as x minus expectation of x given y. Okay. Now, this is a random variable, x is a random variable. This one is a function of y. This is a function of y. Now, y is also a random variable. For a given y, this is the estimate we get. But we can get many y's, right? Many possible y's can be obtained. So, this is the estimation error. What is the mean of the estimation error? To find the mean of the estimation error, we need to use the expectation of epsilon. The expectation of epsilon means expectation of x and then the estimate. This is the estimate. Okay, now we can, because expectation means integration, and we know that we can do the integration separately for each of these two terms. So we can do expectation of x and then expectation of x given y. Now I gave a homework problem where you need to show that this is actually expectation of x. So the expectation of the estimation error is 0. Such an estimator where the mean of the estimation error is actually 0 is called an unbiased estimator. We want all estimators to be unbiased, and minimum mean square error estimator has that property. It is an unbiased estimator. So this indicates that the expectation of the actual variable, which is E of x, is equal to this one. This is the expectation of the estimated quantity, right? The estimate. E of x given y is nothing but the estimate, and we are doing expectation of that. So expectation of the estimate is the same as the expectation of the actual variable. Okay, that's why the estimation error is expectation of the estimation error is same. So an estimator which has this property is called an unbiased estimator. Okay, estimation error variance is also an important parameter of the estimate. Estimation error is epsilon. Estimation error variance is what? So if you go by the definition of variance, it has to be this squared and the whole thing will have this expectation operator. Now we know that this is equal to 0. So estimation error variance is nothing but this one. Right? So you can write x minus E of this one. Right? Now here we have two random variables x and y. This is the estimate given a particular y. But when we are doing expectation of the whole thing, we have to treat both x and y as random. So this one is actually now the inner one, inner integration, you can write as the conditional variance. Inner integration is the conditional variance because here we are actually, this is the for variance we need to square the whole thing, right? And since the PDF, corresponding PDF we have taken as the conditional PDF, the variance is conditional variance. And then the whole thing again has to be integrated with respect to y. Then only we will get the estimation error variance. Now, if you refer to the example that we considered in the class, you will find that this is not a function of y. It has only sigma terms. So you can take this outside the integration, and then integration with respect to y is unity. So in the example that we considered, the the estimation error variance is equal to the conditional variance. But that is not the case always. Okay, if the conditional variance is also a function of y, there, then you need to do the integration properly, and that only will give you the estimation error variance. Okay. Now, another desirable property of an estimator is efficiency. What is an efficient estimator? An efficient estimator has the lowest estimation error variance. Okay, but what about MMSE? Is it an efficient estimator? Now let's consider another unbiased estimator, and its estimate is exact. So what is the estimation error? Estimation error is this, and estimation error variance is this one. We have considered an unbiased estimator, meaning expectation of x is actually expectation of x hat. So estimation error is 0. So the mean of the estimation error, the expectation of the estimation error is 0. So this is the estimation error variance for that estimate. Now we already derived the expression of the minimum mean square error estimator by minimizing this one, right? So you got an expression of x hat by minimizing this one, right? So from this we can say that MMSE is an efficient estimate. Okay, so two important properties of any estimator are that they should be unbiased, desirable properties, and to the extent possible, we want an efficient estimator. And in the case of MMSE, we see that it is an efficient, it is an unbiased estimator, and it is also an efficient estimator uh, if we consider all unbiased other types of unbiased estimators. Among all unbiased estimators, MMSE is an efficient estimator. Okay. And also the properties that we discussed in the context of that example hold here. It applies appropriate weight to both measurements and prior information. And that disadvantage is that the estimate is not necessarily a linear function of the measurement. Okay. So that's all about MMSE, and we need to stop here for today. Tomorrow we are going to look at other estimators, weighted least squares. First we'll derive weighted least squares estimator, and then we have the linear MMSE. So we'll apply the linearity constraint on the expression of x hat, and then derive the linear MMSE estimator, which is a linear function of y, and at the same time also has an important property of the MMSE. Okay, using a particular property of MMSE, we are going to derive that. Following this, time permits, we'll do a simple example where we'll see how to apply these estimators to estimate an unknown quantity given some measurements. And then the only thing that we'll have is the calculator. I will not derive the calculator as I told you earlier. We'll just note down the expressions, the equations, calculator equations, and then if possible we'll discuss some properties. Okay, that's it for today.